Okay, so the Skydiver project, you got, should have that ready. You got your plane here and your person falling out of the plane. They're coming down. We're going to draw a free body diagram here. We'll have the force from gravity, the weight pushing down, and then we'll have some drag force. I'm going to call this capital D, pushing up. Now, in your project, you're going to need to draw a free body diagram. You don't have to make it professional looking. Like what I've drawn here is perfectly fine. You can just hand draw this and insert it into your paper. If we were doing this, like if we were actually going to publish a paper, then you would make this free body diagram professional looking. Don't worry about it here. Something hand drawn is fine. But make sure you include a free body diagram. Make sure you explain the physics that I'm about to explain for how we get the differential equation. That's where you're going to start. So we've got weight pushing down, some drag force pushing up, and that drag force is some drag coefficient times v squared, where beta is 1/2 rho A times some CD. A here is the cross-sectional area of your skydiver. Rho is air density. You're going to explain all of this to your audience in your paper and in your presentation. And CD is the drag coefficient. Now you got to be careful. If you were to just Google drag coefficient, some sources will list this number here as the drag coefficient. Other sources will list this guy that takes everything into account as the drag coefficient. So when I say drag coefficient, at this moment, I'm talking about this guy right here. This depends on what kind of material you're wearing, what orientation your body is in. We have different drag coefficients. Spheres have a different drag coefficient than rectangles or whatever. So this is material and shape dependent. This here takes everything into account. So we're going to call this our drag coefficient. Okay, and I'll tell you what numbers to use for all this. I'll show you in a minute. But for now, we're going to squish all this together and call it beta. And then the drag force is proportional to v squared, your velocity squared. Okay, then Newton's second law, the sum of the forces should equal mass times acceleration. And we know what our forces are. Our weight is pushing down, so that'd be a negative mg. And then our drag force is pushing up, so plus beta v squared. But we know acceleration is just the second derivative of position. So this would be my second derivative equals negative mg plus beta v squared. So we have a second order dE. But wait a minute, I've got a y and a v in here. But remember, v is just the first derivative of position. So y prime squared. This is a nonlinear dE. I've got y prime squared in here. Now, a lot of times it's a little cleaner if we divide through by this m here. So I'm going to do that, get rid of this m, and call this y double prime equals negative g plus beta over m y prime squared. This is the DE we're going to be solving. It's kind of challenging to solve this. It's a second order nonlinear DE. It's actually easier to solve for V instead of Y. And then once we get V, just integrate that to solve for Y. So again, recall, it says recall. Let me write that better. Recall, V is just Y prime. So V prime would be Y double prime. So I could make this V prime equals negative G plus beta over M V squared. It's still nonlinear, but now it's first order. Going to be easier to solve. In fact, it's separable. This is a separable DE. And that's how we're going to solve it. Now, it's not that it's a hard DE to solve. It's just there are a lot of moving parts. It gets kind of nasty. And I have solved this 3 or 4 different ways. I am still not convinced whether it's better to bring the M over, maybe multiply both sides by M over B to make this a 1. It's going to get nasty no matter what we do. Let's write this in separated form. So remember, V prime is just dV over dt. That'll equal this. I want all my V's on the left, all my T's on the right. I could rewrite that as dV over, and I'm going to swap the order here just to put that V squared in front, equals dt. So now we've separated the variables, and we just want to integrate both sides. So now integrate. We got to do a partial fraction decomposition on this. This is where it gets ugly. I want to write this. I want to write 1 over beta over m v squared minus g. Think of this like a difference of squares. So this would be square root of b over m v minus root g times root beta over m v plus root g. So that's just the left-hand side. And again, sometimes I think it might be easier if we turn this into a 1 by, multiplying through by the appropriate fraction to make this a 1, but then you get a nasty fraction here. So you got to deal with this weird, radical, weird fraction thing no matter what. Okay, we're going to write this as some A over that first guy. I'm going to show you what your solution will look like when you're done. In fact, I'm kind of going to show you all the steps in a previous, lost my V there, a previous group's solution. So I got to do the partial fraction decomposition here and find A and B. Then to integrate, both of these are just going to be, we're going to do a U sub on them. They're both natural logs. So we get like a log of junk plus another log of junk, and we squish our logs together. It turns out one of them's negative, so you get a log of a fraction, and so forth. So this is the hardest part of the project, is once you get here, solving this integral here. Now I'm going to show you what you actually end up getting. Okay, so you're going to do your partial fraction decomposition. This group didn't show all the work doing the partial fractions, but this is what you're going to end up getting. So I think I called the minus one the A and the plus one the B. So M over 2 square root of mg. Oh, this group here. Yeah, they did multiply top and bottom by m here. So that instead of having b over m, you'll have m on top. And then you won't have a fraction here. Again, I've done this both ways. I'm not sure one way is better than the other. If you do it like this, so that's again multiplying top and bottom here by m over 1 so that you get m here, b v squared minus mg. Might make it a little cleaner. Then this will be your a, this will be your b with the minus in there. And now you got to do an integration using u substitution. You want to show more steps than this group did. You'll end up with this after you do your integration, something like this. On the other side, the antiderivative of dt is just t plus c. Then you squish your logs together. Now, our goal here is to solve for v. So you want to get that v by itself. So make both sides powers of e. And then we can incorporate this. We'll have an e to the junk. And then you get this plus c up here. You can incorporate all of e to the c into a new c. So this c is different from that c. Now, again, we're trying to get v by itself. So now we have to algebraically solve this for v. So cross multiply. And then you want to collect like terms, get v by itself. There are several steps in there. Again, this group should have shown more steps, but like that's your job is to figure out all these steps. You're going to end up with something that looks like this. Now we got our Skydiver here. We're going to assume v of 0 equals 0. And we're going to assume y of 0 is some realistic height. Let's say 1,000 meters. Maybe we'll change that number, something realistic here. Okay, so once we get to here, we have to solve for capital C by plugging in our initial condition. And if you've done it exactly the same way they've done, you end up getting C equals -1. And this is your final solution. This is V. Okay, now what are all of our constants? Air density. This is not actually constant as we're falling. This actually changes. You know, air is less dense higher up. This group in particular considered making this project harder by making air density here a function of height. And it just turned out to be too nasty. And air density didn't change that much that it made a substantial difference. So we're going to make the assumption here, the false assumption that air density is a constant for the entire fall. And this number is what we're going to use. This is the cross-sectional area of a skydiver in the prone position in that kind of position. CD here, our drag coefficient is about 1. We know G is 9.81 meters per second squared. So now we can calculate beta. And once we put in all of our constants, this is our final solution for velocity. So you're going to go through all this and you're going to show all those missing steps that this group left out. Like you can use this as a template here, but show those missing steps. You're going to produce a graph. I would recommend using Desmos to produce a graph here. Make sure you label your axes. Remember, all of our velocities are going to be negative here. because up is the positive direction and down is the negative direction, and we're moving down. Velocity tells you which way you're moving. So we're going to start at zero and we're going to be approaching what's called terminal velocity. You want to discuss terminal velocity a little bit, and that's the number we're approaching as t goes to infinity. And in using all the numbers we've got here, it's going to be negative 47. We can see that here if we take the limit as t goes to infinity. You actually have to do the easiest way is L'Hopital's. If you use L'Hopital's on this, you'll see that this limit here as t goes to infinity is negative 47. Okay, now for some reason this group wrote this line here. You never reach terminal velocity. You asymptotically approach it, but you don't actually reach it. That I like that they included the blue line here to show what we're approaching, but don't write this line. You never actually reach terminal velocity. Okay, so once you get V, you're going to draw a graph. Remember, the entire point of having a graph is to discuss that graph. So then you'll write a little blurb, write a couple sentences. Like I would just alter this and say, we can see here the Skydiver starts with a velocity of zero, and after 10 seconds is within 1% of terminal velocity, or whatever that number is. Figure out that percent difference there. Something like that. Tell us something about what we're seeing in this picture. Okay, now that we've got velocity, we want to find, go back to mine. So let's right here, get V of t, graph, talk about the graph. Now we're going to get Y of t, which is just going to be the antiderivative of V of t dt. And we have our initial condition with Y of 0 equals, and you know what, we'll use the same initial height that this other group used so that you end up getting the same numbers. You can see all their math here. Again, you're responsible to figure out all this math. Oh, they okay, maybe this isn't reasonable. They used an initial height of 10,000 meters. Remember, we're in SI units here. That would be like 30,000 feet. You planes fly that high, but skydivers do not jump from 30,000 feet. This is too high. So, we do use like 1,000 instead of 10,000. So you're going to get a different value for C. You can get a slightly different Y of t here. So again, you can scroll through here to see how you're going to integrate this. You're going to use a U sub. The best way to do it is split this up 1 over junk, something like this, and then minus e to the junk over junk. You split it up. This one's just a simple U sub. This will be your U, and then your du will be right here. For the one that looks like this, multiply top and bottom by e to the negative junk. So you end up with e to the negative junk, then on the bottom, e to the negative junk plus 1. And then your u is the bottom, your du is on the top. Same thing here. I want to make sure I said this right. Your u here is the entire bottom, du is the top. Okay, they made this more complicated than it needs to be. Okay, maybe I'll write some of this up just to make this more explicit. So, yeah, you're not going to have exactly the same kinds of terms here, but you're going to get something like V. Here, that's right, isn't it? You can get Y is some kind of integral of e to the Let's call it AT. Was it who's on top? Plus or minus? Minus on top. Again, there will be a lot of details I'm not going through here. That's what your job is in the project to figure that out. So we're going to split this up as the integral, something that looks like this, and then something that looks like this. Bring that minus out. Okay. On this one, u equals 1 plus e to the at dt. Then du will be e to the at dt. So I'd have to put in an a and take out an a so that this is my du. And we get something that's kind of like negative 1 over, or negative 1 over a, u 1 over u du. And it's just a natural log of u. And you're going to have some extra constants hanging out. On this guy, you're going to multiply top and bottom by e to the negative at. So I'll get e to the negative at plus 1 dt. And then same game here. U equals the bottom. Then du is negative e to the negative at dt. And you'll get like the same kind of integral. You get a 1 over u du. You end up with a log. You'll squish them together and so forth. Okay, so you're going to solve for y. Again, use y of 0 equals 1,000 meters. You're going to graph y and then find when we hit the ground. Find when y equals 0. And then figure out what the speed is at that time. So once you get that, let's call it t1. Find v of t1, the speed when we hit the ground. The velocity. You're going to get a negative. It's going to be about negative 47. Now, of course, this does not happen what happens in the real world. You don't fall the entire time. You would deploy a chute, but this project's long enough as it is. It's complicated enough as it is. We don't need to worry about a chute. Now, I do need to point out that out of all the projects you could choose, this one is the most challenging. This is the hardest of the projects. It's also the most interesting. I've shown you basically how to do all of project one. It's when we get to project two that you take this same scenario and we apply numerical methods to it. That's when it gets a little more challenging because of that v squared. We're going to have to square a power series. So on project two, it's going to be a little bit challenging. Honestly, probably not much harder than what we're doing here, but just be aware of that. This is one of the more challenging projects. Okay, so you're going to type all this up in a paper. It's going to look, a lot like this paper here. You're going to have graphs. You're going to type up all your own math. All the math must be typed up. I'll show you the best way to type up math. Then you're going to produce a slideshow. Every single detail is in the paper. The paper covers everything. The slideshow is just the highlights. So we're not going to walk through all the gory details in the presentation. We're just going through the highlights. Nothing should exist in the slideshow that's not in the paper. Nothing at all. We're just going through the highlights. So what am I going to cover in the slideshow and in the presentation? You're going to quickly walk us through the physics. You're going to, again, have a free body diagram, show that in your slideshow. Here, I should put units on V of 0. This is meters per second. Always have units. So you're going to have your free body diagram, quickly explain the physics. You've got a weight pushing down, a drag force pushing up, where the drag force is proportional to V squared. So here I really should say magnitude. And proportionality constant, we're calling beta. You quickly, like I'm talking, so far we've been maybe 30 seconds into the project. You want to get to here within maybe a minute and a half, 2 minutes at the tops. You don't want to waste too much time walking us through background stuff. So basically all the stuff I did here at the beginning, quickly get us there. If you want to tell us what all these numbers are right at the beginning, that's perfectly fine. If you want to carry around numbers and solve all this with numbers everywhere, that's perfectly fine also. I think it's a little easier to solve it symbolically and then plug in the numbers at the end. So get us to here. On the slides, do not overwhelm your audience with too much information on any slide. You never ever want a big old chunk of math on one single slide. People won't listen to you. You're trying to talk to them and they're trying to read the whole thing. It's better to have a bunch of slides with just a little bit of math on each. The number one rule for your presentation is do not read to your audience. Don't read text, don't read math. Everybody's voice sounds terrible when they're reading. Nobody wants you to read to them. Never have a big chunk of text, never have a big chunk of math on your slides. Just talk. Have maybe a couple of pieces of math on a slide and just quickly talk us through them. Okay, so you quickly, within a minute or two, get us down to here. And you're going to say, hey, this is the first order separable dE. Let's separate the variables. So maybe you would jump from there to here. And you would just quickly say, okay, well, okay, we probably want a slide with this. So I have a slide there, a slide here, and then just say, okay, multiply the dt over, bring this down to the other side. Okay, we're going to solve this using partial fraction decomposition. And again, I'll leave it up to you if you want to do like that other group did and multiply top and bottom here by m over 1. I find it easier to do with this version. Either way. Again, do not have a whole bunch of math on one slide. Like all of this, where are they doing the partial fractions here? You would not want all of this on one single slide. It would look terrible. You do not want to read a bunch of math to your audience. Do not do this. M over 2 square root of mg integral 1 over square root bv minus square root mg dv. You're already bored. Now imagine that going on for 6 minutes straight for one single slide. Do not do that. Don't read to your audience. Everybody, whoever is presenting, should have control of the mouse. Look at my mouse on the screen. If you're the one presenting, you need to have control of the mouse and you point to stuff and you quickly go through it. Again, in the paper, you're going to go through more details than this when you're doing your partial fractions. But then during the presentation, just show the highlights. Okay, look, we're doing partial fraction decomposition. We're going to assume that this can be split like this. See the paper for all the details. Here's what we got. And then next slide, show what you got for A and B. I don't know that you need to walk us through all the algebra to do the partial fraction decomposition because that's incredibly boring. That's what the paper is for, with all those boring details. Now we're going to talk about how we're going to integrate this. So quickly, you'll just go through the U sub. So maybe have a slide. Like again, this group should have done more here in the paper, but maybe have a slide for this integral here where you say U is this, du is this, but just point to it. Don't read the whole thing to us. Hey, you can see here we use this for U. Here's our du. Here's what we get when we integrate that. Similarly, a slide to get from here to here. But go through it quickly. And then you do want to walk us through a couple of details here because there's some interesting stuff going on here. Like we squish these logs together because the difference of logs subtracted outside becomes divided inside. We make both sides powers of e. See, I'm just going through it without reading the whole thing to you. And then again, this group skipped the details here in the paper, how to get from here to here. Definitely have that in your paper, but quickly go through it in the presentation. Same thing here. So maybe we're 6, 7 minutes at most into the presentation. Remember, your presentation is going to be 10 to 15 minutes long. I would rather see a 9.5 minute presentation than a 15.5 minute presentation. It's better to be a little bit too short than a little bit too long. If you were presenting at a conference and you went over your allotted time, they would never invite you back. Never ever go over. Definitely do not go longer than 15 minutes. Shoot for more like 10 or 12 minutes, something like that. Okay, so you get your V, quickly talk about, solving for your constant of integration here. At some point, you're going to have this on the screen. Show this graph, and you might spend a good 30 seconds just talking about this graph. I mean, obviously, you've made your own graph, but the entire point of having a graph is to discuss the graph. Well, we could see here that we start at 0 and we're approaching terminal velocity and so forth. Okay, then we're going to move on to y, like all the same stuff. Like just repeat everything I said. Don't spend too much time on the boring details, but show us all the interesting parts. And don't read a bunch of math to us. It's okay just to point to stuff and say, oh, we use this as u, so here's our du. Again, whoever wrote this up, this is written up really weird. Don't write it like that. Like just this line here looks weird. That's the alternate way to do integration by substitution, and this one I've never liked it. Anyways, like it's okay to just point to stuff and say, okay, like for example, we're doing this integral here. Here's our u, here's our du. When we integrate, we get this, whatever you get. And this is written up so weird. So I guess here is our final answer. And then show a graph of y. I would definitely show a better looking graph, like zoomed in just for this region. You're not going to get 200 because we're using a different height. Like none of this makes any sense here. We're never going to go negative, so don't include it in the graph. Spend a little bit of time talking about the graph. Show how long it takes to reach the ground, find the velocity at that time, and then wrap it up. And don't end your presentation with, and that's all we got. end it with, and that concludes our presentation. If anyone has any questions, please feel free to see our paper in the discussion board. And thank you for your time, or something like that. Okay, how are we going to type up the paper? I highly recommend Google Docs. You guys all know how to use Google Docs at this point. Okay, in Google Docs, you can actually type math. Do not use Microsoft Word to type up your math. It takes forever. Most of you are engineering majors. At some point, you're going to need to learn LaTeX. So I recommend this extension called Auto LaTeX Equations. My phone is going off here. So add on that extension. Oh, I already started it. It looks like this. And now I can just type math. I can type my paper. The differential equation is. Now, if I want to type math, I need to enclose the math in these dollar signs. So, like, let's say we had MV prime equals negative MG plus beta. I get beta like that, V squared. Now, you may have to Google how to type out some things in LaTeX. Like you may not have known how to type beta, or you might just want to call it capital B, but I like beta better. And then I can hit render equation. And oh, I may have lied to you. If you mess up, go back to the beginning, hit derender. I think it's just lowercase b here. There. Now, you don't have to render each equation as you come to it. You could literally type up your entire paper, hit render at the end, and it'll go through and render all of your equations. I don't recommend that though, because you're going to make typos. Do a couple, like type a couple of paragraphs, maybe a little bit of math, 3 or 4 equations, hit render, check them, and move on. Okay, once you get everything typed up here in Google Docs, there's no need to reinvent the wheel. I can now use Google Slides. I'm already signed in, but to make my presentation. Listen, your fancy transitions and your backgrounds, I could not care less about any of that. Please do not spend a whole bunch of time making the presentation look fancy. It's not going to earn you any extra points. Like if you want to, you can. If you want a bunch of fancy backgrounds and transitions, it's fine. I'm not going to take points off for it, but I don't want you spending a bunch of time on that because I could not care less. I just care about the content. Now, you can type math here in Google Slides. It's possible. There are even extensions. Like I don't use this one. I forget which extension I use. I think I use this. But I find it more trouble than it's worth. We've already over here typed out all of our math. Just copy it over. So I can just highlight that guy. Yeah, Control C over here, Control V, boom, I'm done. Now I can move it where I want it, resize it. I got my math in here. So that's what I recommend. Type up all your math over in Google Docs and just copy over the part you want to present. Remember, everybody has to present. Remember, everybody is responsible for the entire project. I know you're going to split up the work somehow. You'll decide as a group how to split up the work. I'll give you a suggestion. I would say one person maybe is in charge of all the math doing it all by hand. And then they send that out to everybody to double check and verify. Then somebody else is responsible for typing up the paper. Then another person might be responsible for doing the slideshow and producing all the graphs. And that's if you have three people. If you got four people, the fourth person maybe helps everybody else. I don't know, figure out as a group how you're going to split up the work. But whoever is typing up the paper, you're going to need to get that typed up before the slideshow guy has a chance to do anything because you're just going to copy in here. So this is not a hard job making the slideshow. That's why you got to do extra stuff also. That is not a full contribution, just doing the slideshow. But everybody's responsible for the entire product. So do not think, okay, well, I'm responsible for slides one, two, and three, and I'm going to get graded on one, two, and three. No, you're graded on the entire project. And I'm going to talk later about like the multipliers and what to do if somebody doesn't do their part. We'll talk about that in general with the entire class. But everybody is expected to double check everything. Work on this early so that you have time to double check everything and everybody's happy with the final project. Everybody has to present. You're graded as a group on the entire project, and you're graded individually on your own presentation. If you read to the audience, you're going to get a terrible grade. That's my number one pet peeve. Do not read to me. Do not, let's find a place with words. We can see that the velocity values are all negative because our skydiver is falling down. His speed initially increases linearly as good. That is so boring. I don't care if those words are on the screen or not. Sometimes people will have note cards and they think we can't tell, but they're clearly just reading to us. That's terrible presentation style. Don't do that. You have a mouse. Whoever's presenting should be in control of the slideshow. Point to the stuff you're talking about. Use it as a little laser pointer. Okay, I think I've covered everything. Yep, I think that's a good place to stop.